Okay, so this is a third problem of week number 11, which is a kinetic molecular theory of the gases. And then they ask to calculate root mean square speed of carbon monoxide gas. So root mean square, in short form, this is called RMS, and the root mean square speed, and this is known as VRMS. And if you look at the equation that is shown up here, this is the formula that people are using it. So this is 3RT over M, and that's the unit. And you have to be careful in using plugging the right numbers to get what kind of value that you are going to get. So I am going to actually emphasize, even going to talk about the kinetic theory. Let's just talk about the MKS unit. So each scientific unit must have a length scale, which is a meter, and mass, which is a kilogram, and which is a time, which is a second. Okay, so those are the three fundamental units. And then when it comes down to, if you use anything related to the mass, length, and the mass and the time in this MKS unit, your force unit ended up being Newton. Your energy unit ended up being Joule. And so on. So therefore, for example, like for pressure, which must be a Newton per square meter, and this is people also call Pascal. So this is all interrelated one. So having said that, I have to choose this. Let's try to think about this 3. I don't have to worry about it. R must be a value that I must choose wisely, and then this is something that T must be a unit of the temperature. So this is degree C, it must be a unit in the Kelvin. So my choice is here. Let me just say that R, you want to use the value called 8.3145. And if you look at the unit, it says a joule per mole Kelvin. So that's the unit. This is different from 0.00821 mole on the ATM liter divided by mole Kelvin. Okay, so the energy unit in the numerator is a joule, and so therefore all the units that I have is now can be understood in the following. So what I'm saying is, if you use this one, the unit of speed must be length divided by time, which is a meter per second. And also, obviously, this one must be unit of Kelvin. This mass must be in the unit of kilogram. Okay, so carbon monoxide, we know this is 28.01 gram per mole, but we cannot use gram. We have to use in the unit of kilogram, and then everything will be okay, right? Okay. So let's see this. Let's do this way then. So first of all, the carbon monoxide, CO. So molar mass is known for the CO is 28.01 gram per mole. But what I want to use is, I cannot use the gram. I need to change it into the kilogram, which is 0.02801 kilogram per mole. So then this number that I can plug it in for the average speed, root mean square average speed. And the number 2, obviously temperature, is a degree C plus 273.1 and it will be unit of Kelvin. Okay, so having said that, I can do the following now. So, what is my at 25 degrees C? So, therefore, VRMS is, once you know the MKS unit, it's pretty straightforward. 3 and the R, which is 8.3145, and the T, which is 25 plus 273.15. Okay, carbon monoxide is here. That's an equation, and then divide this by essentially 0.02801 kilogram. Okay, that's all there is. So if I want to show you what I did is, that is a unit of kilogram, that's a unit of Kelvin, and this is a joule per mole Kelvin. And then this is a kilogram per mole. So therefore, the unit all works out, and then I ended up getting this one to be 515, and the unit is meter per second. Okay, so that's at 25 degrees C. Okay, so I can do the same thing here, number 2, which is at 100 degrees C. So VRMS at 100 degrees C is 3 times 8.3145, 100 plus 273.15 divided by 0.02801, and that will give me the value of 576 meter per second at 100 degrees C. So now you will notice that upon the temperature increase, your average speed is going up. So, and there is a graph that people use to describe this. So, in the kinetic theory, the gas molecule has a speed distribution, and then this is a number of molecule, and so this is their speed distribution. So let's say this is a 25 degrees C, and if it's 100 degrees C, it is more like that. Okay, so then that's 100 degrees C. On the average, the peak position is moving to a higher velocity, and we can calculate those. So the higher the temperature goes up, the root mean square averages is going to go up as well. And then actually you can simply predict this by understanding this, where the molar mass is constant, everything is constant, so it's actually root mean square is proportional to the square root to the temperature. So this is something that I can say. I also look at the literature to show you some of the more information. This is a speed distribution. This is a speed distribution, right? So this curve, the x-axis here is what is known as a speed. Y-axis is going up by knowing the number of molecule. Is how many number of molecules are there. So this curve itself is a speed distribution, and there are actually 3 different types of averages. First one is called the most probable speed. We call the speed with a p at the end. That's where you are at the maximum, right? So that your distribution is at the maximum. The root mean square has a meaning of your velocity was the speed was squared, and then the doing the average value on that, and then do the square root on it. And that's what we call the root mean square velocity. The average velocity is somewhere in between. This is called the average, AVG. And then that's in the mathematically, they just do the measurement this way. Okay, so this is a notation that when you take the averages, and then you will learn this one when you are in the junior in the taking a macro physical chemistry. You know how to get those equations from the kinetic theory of the gases. So the speed distribution depending on the temperature, and for a fixed temperature, molar mass, depending on how heavy the molecules are, the speed distribution is really fixed. So temperature is essentially proportional to kinetic energy of gases. And as the temperature goes up, as you can see that the average velocity, average speed of the gas is moving to a higher speed. And for a given temperature, the lighter, right? The lighter gas is moving faster compared to the heavier gases. And as you already know, that RMS, we talked about it, inversely proportional to the molar mass, right? So we can see that how fast the gas can move is inversely proportional to the square root value of their molar mass. Thank you for your attention. It's a long story, but simple answers. And then actually the really tricky part here is understanding that here I want to use the gas constant to be in the unit of joule per mole Kelvin. So having said that, joule is my energy choices, and naturally require for you to use meter, kilogram, and second as a choice of your length scale. Okay, that's a recap, and then hope you can have a better understanding about how to deal with these numbers in this equation.